Assalamu alaikum, my dear students of Pharmaceutical Analytical Chemistry 1. Today we are continuing our online practical session, which is about the quantitative determination of mixture of acids. In earlier session, we had it online. We explained all the theoretical aspects of this practical. Now we are going to proceed in doing the practical experiments. Before we start, we have to fill up the experiment design, which starts by titrant preparation. So we have to prepare 250 ml of 0.1 molar sodium hydroxide solution. Then we have to proceed with the standardization of the prepared sodium hydroxide solution by using 0.2042 gram of potassium hydrogen phthalate powder. And then we have to fill up all the titration components. Then we will do the actual experiments and start calculating the molarity of the sodium hydroxide, which is our titrant for today's experiments. Next, we have to start with taking 10 ml of the mixture of unknown acidic solution, which is composed of hydrochloric acid and acetic acid. And then we have to continue as before to fill up the titration components and find out what is the molarity of HCl and what is the molarity of acetic acid in that sample. So first of all, we have to start by doing the calculation of the titrant preparation. So he is asking me to prepare 250 ml of 0.1 molar sodium hydroxide. As we agreed in the practical sessions earlier session, we have to find out first what is the sodium hydroxide and if it is available in the lab in form of solid or liquid. Actually, I get it in the lab in form of solid particles, as you can see here. So this is the sodium hydroxide pellets. Okay, for the sodium hydroxide pellets, we have to use the following equation. So the molarity will be equal to weight subdivided by molecular weight per each 1000 ml of solution. Okay, so what is the unknown in that equation? The unknown is the weight. We want to know exactly what is the amount of sodium hydroxide we are going to take to prepare that solution. So we will say that the weight will be equal to molarity, which is 0.1, which is the one I want to prepare, multiplied by the molarity of the sodium hydroxide, which is 39.99 gram per mole. This number we can find it even in the bottle. You'll find it here mentioned 40, which is approximate number, but the exact number is 39.998 gram per mole. You can calculate it from the molecular math or just get it from Google. Okay, so the weight of that, it would be 3.994 gram. But this amount is needed to prepare 1000 ml, and actually we need only 250 ml, which is quarter this amount. So simply we will subdivide this number by 4. So the needed amount, it would be 0.999 gram of sodium hydroxide pellets. Okay, to prepare it, we have to get a volumetric flask with the total capacity of 250 ml. Then we are going to place this amount of sodium hydroxide pellets inside it. Then we are going to fill it up to the mark of 250 ml using for sure distilled water. After continuing that, of course, we have to add sodium hydroxide, and then we have to add a smaller amount of distilled water and try to dissolve the amount of sodium hydroxide slowly. Then we will have to add another amount of water, distilled water, and to try to dissolve the amount of sodium hydroxide once again. And so till I reach to the maximum capacity of 250 ml, then I have to simply close the volumetric flask and store it till I proceed with the second step. Okay, so for the second step, I have to standardize the prepared sodium hydroxide solution using 0.2042 gram of potassium hydrogen phthalate. First step before proceeding in such reaction or in such experiment, we have to write the equation, because as you know from the theory or the theoretical part of the practical, that we have to know what is the stoichiometric factor, and knowing the stoichiometric factor, we can get it only from the equation, balanced equation. So this is the structure of the potassium hydrogen phthalate. We are going to react this potassium hydrogen phthalate with our titrant, which is sodium hydroxide, which is, in that case here, we will consider it as an analyte till we get sure about the concentration of the sodium hydroxide. So the outcome of that, it would be, or the products of the reaction, it would be as following. In addition to water. This is simple reaction. Okay, so now we will go to the stoichiometric relationship between the titrant and the analyte. The titrant in this stage of the experiment, actually it is potassium hydrogen phthalate. So here we have 1 mole of potassium hydrogen phthalate, which will react with 1 mole of sodium hydroxide to produce 1 mole of the potassium sodium phthalates and 1 mole of water. So the stoichiometric factor here, it would be 1 to 1. The titrant of today's experiment, it is potassium hydrogen phthalate. I will abbreviate it like this. And from that potassium hydrogen phthalate, I will take 0.2042 grams. For the analyte, it would be sodium hydroxide solution, which is the one we prepared in the first stage of the experiment. So the analyte is sodium hydroxide solution. We'd like to know the molar concentration of that solution. The indicator in that case, we can use the phenol phthalate. So this is the phenol phthalate indicator, and from that we will take from 3 to 5 drops. Specific conditions, we usually do it if the experiment needs heating or proton donor or any other specific condition which is not applicable in today's experiment. So the titration system layout, we have to draw it, so we will do the practical in quicker and precise way. So here in the pipette, I will put the sodium hydroxide solution, and in the conical flask or the Elmeyer flask, I will place 0.2042 grams of potassium hydrogen phthalate. This solid amount of potassium hydrogen phthalate, I have to dissolve it, so simply I will add 10 ml of distilled water. And I will add the indicator, which is phenol phthalein, as we agreed here. Later on, I will proceed with the chemical experiments, but I have to fill up the other experiments as well, the other components of the experiments. So here the equation, which is between the titrant, which is now sodium hydroxides, and the 2 analytes of HCl and acetic acid. And the equation would be as follows. So HCl plus sodium hydroxide, it will give us sodium chloride plus H2O, and acetic acid, which is CH3COOH plus sodium hydroxide, it will give us CH3COONA, which is a salt in addition to water. If you can notice here, the stoichiometric factor between the HCl and sodium hydroxide, it's once again 1 to 1. And the same for the acetic acid and sodium hydroxide, the stoichiometric factor, it is 1 to 1. For the titrant, the titration component, the titrant in that case, it will be sodium hydroxide solution, which is the one we already prepared before, and we get the exact molar concentration of it. For the analyte, it will be the mixture of acids. And for the indicator, it would be again phenol phthalein. For the specific condition, we don't have any specific condition for this chemical reaction. For the titration system layout, for sure in the purette, we will have sodium hydroxide solution, the standardized one. While in the conical flask here, we will have 10 ml of the mixture of acids, of mixtures. Okay. In the first trial, we will do the experiment using phenol phthalein as an indicator, while in the second trial, we will use methyl orange as an indicator. So here, once again, it would be sodium hydroxide, and it would be 10 ml of mixture of acids. We will determine the end point in that experiment, which is number 1 and in number 2, and then we will fill up these places. Then we will try to calculate the molarity of HCl and the molarity of acetic acid. You know, phenolphthalein as an indicator, it can detect the end point of both reaction of HCl and sodium hydroxide and of acetic acid and sodium hydroxide. While in methyl orange, this indicator, it can detect the end point only of the HCl and sodium hydroxide, but I cannot detect the end point of acetic acid and sodium hydroxide, as we explained earlier in the theoretical part of the experiment. So whatever the readings we will get from here, it will be used immediately to determine the concentration of the HCl. And then by subtracting these two values, we will get the concentration of the acetic acid. Now we will start the practical part of the experiment. Okay, first step before we proceed with the practical, we have to make sure that all the equipment and the chemicals we need are available at our disposal. So here's our burette with the stand, the glass funnel, Erlenmeyer flask or the conical flask, volumetric flask of 250 ml, small beaker of 50 ml capacity, rubber pipette with total volume of 10 ml, spatula, plastic droppers, weighing paper, in addition to the analytical balance, the water dispenser, and the chemicals we need, which are sodium hydroxide and potassium hydrogenophthalate, in addition to the sample solution, which is a mixture of the acids, methyl orange indicator. I'm not sure if you can see it well because of the light reflection, but yeah, now it's clear, methyl orange. And this one is the phenolphthalein indicator. Okay, before we proceed with the practical experiments, we have to make sure that we are having all the personal protective equipment, including the gloves and the goggles. So I'm going to put them on, and then I will start right now. Okay, first of all, we have to make sure that the analytical balance is well adjusted for well leveled. So we have just to adjust it. It's a little bit difficult mission, but mission accomplished. Now we are sure that the bubble is in the middle of the circle. So now we are ready to use the analytical balance. First of all, I have to use the weighing paper. Okay, so I will open the door of the analytical balance, then I will place it. Then using the spatula, I will take the exact amount of sodium hydroxide. First I have to press on tare. As you can see, the sodium hydroxide particles are a little bit big particles, so it would be so difficult to get the exact weight. For that, we will get as closer as possible, which is 0.9744, but we have to close the door of the balance before we take the reading and wait for the balance to be stable. Of course, we have one limitation with the sodium hydroxide, which is the hygroscopic property of that. If you can notice that the sodium hydroxide particle, they become more shiny on the surface because of absorption of water from the surrounding atmosphere. Now we are going to take this amount of sodium hydroxide and we will place it in the volumetric flask. Then we are going to add distilled water to dissolve these particles slowly. So we will add small amounts, then we will make sure that they are dissolved well. Then we will add additional amount of distilled water, and we will continue shaking to dissolve the particles or the pellets of the sodium hydroxide, and so on till complete dissolve. Now you will notice that most of particles, all the particles of sodium hydroxide actually in the volumetric flask dissolved. So now we are going to continue the volume till the mark of the 250 ml. And to do that, we have just to put it on the table and make our eye level to the same level of the mark. Then we slowly add the distilled water till reaching that mark and make it on the same level of the lower meniscus. So now mission accomplished, and the sodium hydroxide solution is prepared. Of course, if we added few drops or we exceeded the mark of the 250, it will not be that big matter, because in the next step we are going to prepare we are going to standardize the sodium hydroxide. So it's okay if we add just extra few drops, or if the way of the balance was not that much accurate, because the next step of the standardization will make us sure about the exact concentration of the sodium hydroxide. So now the sodium hydroxide solution is ready to be used, and we will move to the next step, which is the standardization of sodium hydroxide. Now we are going to proceed with the second stage, which is standardization of the prepared sodium hydroxide using potassium hydrogen phthalate. So we will get the potassium hydrogen phthalate and the Erlenmeyer flask, or the volumetric flask, the conical flask we are going to use. Using the weighing paper, I'm going to take 0.2042 gram of the potassium hydrogen phthalate. Okay, we went above the required amount, but once again it's okay, because the first trial with the potassium hydrogen phthalate is gonna be rapid titration just to determine the rough end point. So now we will just wait for the balance to be stable. Okay, now we are going to record that reading, which is for the rough 0.226 grams. Make sure that you write everything once you got the reading. So now we will proceed in transferring that amount of potassium hydrogen phthalate into the Erlenmeyer flask. We can wash that amount using the distilled water. as we said, we will need small amount of distilled water to dissolve potassium hydrogen phthalate. So it would be liquid-liquid titration. So now we are ready with that. We will move in preparation of purette. Now we are going to proceed to titration. So as we learned before, the first thing we have to make sure that the entire system is closer to be not that far and not that close. So we will start by cleaning the purette using the distilled water. So we will use this beaker for general cleaning purposes. First of all, we will make sure that the valve is closed. Then we will add distilled water to clean the purette. Then we will allow it to flush out. Next, we are going to clean the purette with the same solution we are going to fill inside, which is the prepared sodium hydroxide solution. And we have to label it first, so we will not get confused with any other chemical in the lab. So we will call it sodium hydroxide solution. Okay. Now we are going to put the funnel, the glass funnel. I'm not sure if the camera can get it or not. Then we will close the valve again, and then we will add a small amount of sodium hydroxide just to make sure that the purette become clean and any reactive material with sodium hydroxide flushed out too. After that, we are going to fill the purette using the sodium hydroxide solution we just prepared. It's very important to make sure that we will not exceed the top of the purette, and we are not going to fill the funnel by huge amounts, so we will lose the control. So now we just filled the purette. Now I'm going to fill the lower parts with the sodium hydroxide. Now it is filled. Now I'm going to remove the funnel, and I'm going to adjust the meniscus on the mark 0. So now the system is ready for me. I have to place white paper here, so whatever the color change will occur, I can notice it very clearly. And this is the Erlenmeyer flask containing our solution, which is potassium hydrogen phthalate solution. Now I'm going to add a few drops of phenolphthalein. Then I will proceed with the titration to standardize the prepared sodium hydroxide solution. I can notice that there is color change, if you can see it. I'm not sure, I have to check the camera if you can see it or not. I think now it would be more clear for you. So notice that when a few drops of sodium hydroxide goes down, it turns the solution pink. It means yes, our system is working. So now we have to go through the quick titration by opening the valve and do continuous shaking, and notice when the color will be changed, at which loop volume exactly. So the color changed, but as we said, this is the rough titration. If we can notice that the volume of the sodium hydroxide consumed, it's around 11.5. So we will do the titration again but we will start quickly. We will go quickly from 0 to 8 or 9, then we will go drop by drop till we reach the exact endpoint. So now once again we are going to repeat weighing the potassium hydrogen phthalate. So we will get the weighing paper, place it inside, close it, just press there. Then using the spatula, we will take the potassium hydrogen phthalate, and then we will add it to the weighing paper. So first thing I have to do is to write the weight of the potassium hydrogen phthalate after stabilization of the balance, and I will call it R1, which is 0.2166 grams. So this is potassium hydrogen phthalate weight. Now I'm going to take this amount of potassium hydrogen phthalate, and I place it in the my flask, and I will use again this water to make sure that the entire quantity are transferred to the my flask. For sure I have to use quantity of water but not exceeding 10 milliliter. To make sure that the endpoints, once happened, it will be sharp endpoints. Now I'm going to add the phenolphthalein indicator. I'm going to put 1, 2, 3, 4, 5 drops. And I'll mark the reading now, which is 11.5. So our start point for the R1 is 11.5. Now we will start titration. We have to make sure that the pinkish color will appear. Yes, it can be appeared. So now we will go down. We said we have to add 9 to 8, so I have to add 9 to 11, so it would be 18. So I will go quickly till around 18. Now I will go drop by drop to make sure that I will get the exact endpoint. It seems that I am too close because the color of each drop is not disappearing quickly, so it seems that we are too close. Yes, we are. So now it is 22.4. Okay, so this is the first reading. Now we are going to repeat the entire process 3 times and take the average of that. After doing the experiment 3 times, we will find that these are the readings. Now I'm going to transfer them to my document here. I'm not sure if it is clear for you or not, but I'll try to magnify it. I think it's okay now. Okay, so this is the flask amounts, first trial after the rough one, so it would be 0.2166 gram. Second trial 0.2163 and 0.2159. The start point here it was 11.5 and the end point was 22.4. Here the start point was 22.5 and the end point was 33.5. 33.3, and here it was 33.3, and it become 44.1. Now I'll find out what is the volume consumed in each trial. 22 minus 11.5, which is 10.9. For the second trial, 33.3 minus 22.5, which is 10.9. Now it's 44.1 minus 33.3, which is again 10.8. The nice thing about the reading that they are very close to each other. It means our results are precise. Now we will find out if it is accurate or not. So 10.9 plus 10.8 plus 10.8 to be equal, subdivide by 3, so this is the average. 10.3, 10.8, 3, okay, 3. And for that one, 0.2166 plus 0.2163 plus 0.2159, yes, subdivide by 3, it would be 0.2162, it means 3 gram, and this is ml. Now, I told you before, you have to train yourself too many times with the calculation, so you have to do the trial one using the numbers of the first trial, and trial 2 by the second trial, and trial 3 by the numbers of the third trial. But just to save time for you, I will do my calculation basing on the average, so I will call this one as average. But please, in your lab reports, you have to do it 3 different times to train yourself more and more about the calculations. So the equation we are going to use to solve this problem, it will be molarity of analyte, volume of analyte will be equal to the weight of titrant, which we know that, subdivided by molecular weight of the titrant, multiplied by stoichiometric factor, which is in this case number of mole of analytes, subdivided by the number of mole of titrant. So the molarity of analyte, this is our unknown, so we will keep it as it is. We will multiply it by the volume of analyte, which is the 10.833. It will be equal to the weight of titrant, which is the average, which is 0.2163. But this amount is in grams, we have to convert it into milligrams, so we have to multiply it by 1000. Then we will subdivide it by the molecular weight of the titrant, which is the potassium hydrogen phthalate. Simply we can Google it, or we can get it from the bottle, or we can calculate it from the periodic table. If we're going to find it out from here, I'm not sure if it is here or not, but sure thing it should be there where it is. I'm not sure, but I can't see it. So I think I will just Google it. So I will ask Google, what is the molecular weight of potassium? Okay. Hydrogen phthalate, potassium hydrogen phthalate, yes. We'll subdivide it by the 204.22 gram per mole. And then we will multiply by the stoichiometric factor, which is the number of moles of analytes, subdivided by the number of mole of titrant. This is the number of mole of the analyte. Where is the analyte? Yes, sodium hydroxide, number of mole is 1. And the number of mole of titrant, which is here, which is again 1, so multiplied by 1 by 1. So the molarity of analyte will be equal to 0.2163 multiplied by 1000, so divided by 204.22, so divided by 10.833. So the molarity is equal to 0.0977 moles. So this is the molarity of the sodium hydroxide we just prepared. Now we are going to proceed with the next stage, which is the titration of 10 ml of the unknown mixture of hydrochloric acid and acetic acid. So here we have the mixture of both of them. Let me first swear the tables. Okay, so we will get clean conical flask or Erlenmeyer flask, and we will use the pipette of 10 milliliters to get 10 milliliter of the mixture of acids. We have to make sure about the meniscus. Okay, now I got the 10 milliliters. Now I'm going to evacuate the content. And now all the content, which is 10 milliliter of mixture of acid, transferred to the Erlenmeyer flask. Now I will get my titration system. No need to re-clean it again because the same solution inside the sodium hydroxide. I will just refill it again to the mark 0. Now I'm going to adjust the meniscus. Now the meniscus is adjusted, and we are now going to start the titration. I will make sure that the camera is shooting everything. Okay. Now I will do the first trial using the phenolphthalein indicator. Okay. So I will take 5 drops of phenolphthalein. 1, 2, 3, 4, 5 drops. 1 drop extra. Sorry. And I will start doing the titration, and I'll find out what is the end point of that. So I can go with the same technique, which is rough titration first, then slow titration, or I can just go slow titration from the beginning. As you can see, each drop goes down, the color keeps to stay. I just want to make sure that you can see everything. Now 1 drop, yes, and the color changed permanently. So now we are going to take the reading, which is 10.4. So first trial, 10.4. Okay, it's exactly 10.4, I'm sorry, so 10.4 milliliters. So this is the trial 1, then I will go to trial 2, then I will go to trial 3, then I will show you the results at the end. So now I'm done with the 3 trials, and here are the numbers. So these are the trials which we got and the readings we got when we used phenolphthalein as an indicator. Now we are going to repeat the entire process by again 3 trials, but in that case we are going to use methyl orange as an indicator. Let's start. Of course, every time we have to clean the Erlenmeyer flask using the water and the distilled water to make sure that there is no remnants from the previous experiments still there. Now it's ready for us. We have to take 10 milliliters, and I have to look carefully to the meniscus. Okay. As you know, it should touch the lower meniscus as it is a clear solution. Now ensure that all the quantity, all the mixture of acids are transferred to the preliminary flask. Then from the methyl orange indicator, I will take 5 drops. Of course, once again, this is totally dependent on the concentration of methyl orange, the number of drops, but it's okay. So I get a new paper because this paper got wet. Now I adjusted the meniscus of the sodium hydroxide, and I will start doing the titration. If you notice the color at the beginning, it was red. Now it's shifted into orange, as you can see. I'm not sure if you can see the color clearly or not. Yes, it is orange. And we got this reading exactly at 5.9 milliliters. So the end point of the first trial is 5.9 milliliters. Now we're going to proceed with second and third trial. Now, after I completed the reaction, now we can see all the readings for the phenolphthalein trial. Okay, if you can see it, this is for phenolphthalein trial, and this is for the methyl orange trial. We will find out that the end point for the phenolphthalein, the average, I think it's around 10.4. We are going to calculate it. And for the methyl orange, the average end point, I think it's 5.8. So now I'm going to transfer all these results into the paper so I can proceed with the calculation. Okay, so here for the phenolphthalein, of course, the flask amount, all of them, in the beginning it was 10 ml. And the average for sure it's 10 ml again. The volume consumed, I will just skip these spaces, so I will go here directly. So it's 10.4 and 10.5 and 10.3. So the average is 10.4 milliliters. For the methyl orange, I'm sorry, I have just to tilt the paper, sorry. Okay, so once again it was 10 milliliters and 10 milliliters and 10 milliliters. Okay, so the volume consumed here with the methyl orange, it was 5.9, and the other one was second trial was 5.7, and the third trial was 5.8 milliliter with average of 5.8 milliliter. Okay. As we discussed before, we said that the methyl orange as an indicator, it have an indicator range around 3.3 to 4.1 or 4. Okay, so within this range of indicator, the end point between the strong base, which is sodium hydroxide, and weak acid like acetic acid, it won't be there. So we will say that the end point of the methyl orange, it will represent the reaction between sodium hydroxide and HCl. While for the phenolphthalein, it will represent the mixture of HCl, the end of HCl and CH3COOH, because as you know, phenolphthalein indicator could be used to detect the end point between the strong base as a sodium hydroxide and HCl and at the same time it can detect the endpoint between sodium hydroxide and acetic acid. So from these measures we have here, we will say that the endpoint of HCl average it's 5.8. So this is for the HCl reaction, while the difference between them will represent the endpoint of the acetic acid. So we are going to calculate it. We will say 10.4 minus 5.8, which is equal to 4.6 milliliter. So this 4.6 milliliter, it will represent the endpoint between the acetic acid and the sodium hydroxide. While this one, which is 5.8 milliliter, it will represent the endpoint between sodium hydroxide and HCl. So when I start by doing the calculation of the HCl, I will take this measure as the endpoint. Okay, so I will proceed now with the calculation. And this is the equation for the titration calculations. Molarity of titrant, volume of titrant, will be equal to weight of analyte, of course in milligram, subdivided by molecular weight of analyte multiplied by stoichiometric factor, which is titrant over analyte. You will notice that the parameters were shifted between the titrant and analyte because we are doing titration, the calculation titration this time. Okay, so let's start. The molarity of titrant is the one we just got it from the earlier experiment, which is 0.0977. So I'll just write it here, 0.0977 multiplied by the volume of the titrant of HCl. So in that case it would be 5.8, which is equal to weight of analyte, I don't know what is that, and the molecular weight of analyte of HCl. For HCl, I think it's around 36, but I will get the accurate measure either from the bottle itself or I will just ask Google. Okay. What is the molecular weight of hydrochloric acid?
The molar mass of hydrochloric acid is 36.46 grams per mole.
Multiplied by the stoichiometric factor. What is the stoichiometric factor between the HCl and sodium hydroxide? It is 1 to 1, as you can notice here. So stoichiometric factor, it will be 1 over 1. Now I will find out what is the weight of analyte using the calculator. It's very simple calculation. 36.46 multiplied by 5.8 multiplied by 0.0977. Yeah. So it is 20.66 milligram. Okay. Now we are going to do the same with the acetic acids. So we will say that molarity of titrant, volume of titrant will equal to the weight of the analyte subdivided by molecular weight of analyte multiplied by stoichiometric factor titrant over analyte. Again, the molarity is 0.0977 multiplied by the volume, which is the endpoint between the acetic acid and sodium hydroxide, which is 4.6. So here it would be 4.6, which is equal to weight of analyte subdivided by molecular weight of acetic acids. I will get it again from the bottle, or simply I will ask Google to get it for me. Okay. What is the molecular weight of acetic acid?
The molar mass of acetic acid is 60.05 grams per mole.
Okay. And then I will multiply that by the stoichiometric factor of titrant over analyte, which is 1 by 1. So it's 1 by 1. So the weight here, it would be equal to 60.05 multiplied by 4.6 multiplied by 0.0977, which is 26.987. So we will 8 milligram, because we said this equation gets the weight in milligram. Now we will go to the last step, which is determination of the molar concentration. So we will convert this weight from milligrams into number of moles. So we will say that we have 20.66 milligram are present in the total amount of the sample, 5 ml of the sample. Where we get this 5 ml, because we said here this is a 10 ml mixture of acid. This 10 ml, we know that it's 5 ml of acetic acid and 5 ml of HCl. So these amount are present in 5 ml of the acetic acid, in the HCl solution, which present within the mixture of both of them. So first of all, we have to convert this amount from milligram into grams. So it would be 20.66 subdivided by 1000. So it is 0.02066 grams are in 5 ml. But we would like to calculate the molar concentration, and we know the molar concentration, it's the number of moles, which is the weight over the molecular weights in 1000 ml. So we want to find out what is the total amount in 1000 ml. So simply we will multiply this number by 1000. Okay, then we will subdivide it by 5. So now we know that it's 4.132 grams are in 1000 ml. So we are going to subdivide this number of weight by the molecular weight of the HCl, which is 36.46. From that we will get the molarity. So subdivide by 36.46. So it's equal to 0.113 molar. Okay. So this is the molarity of the HCl. So this is the first requirement. Let's go to the second requirement, which is the calculation of the molarity of acetic acid. Okay, I'm just checking the battery of my mobile phone. Yeah, it's still full, so we can proceed. Okay. So now this is the number of milligrams we calculated for the acetic acid in the mixture. So once again, it's in 5 ml of the acetic acid solution within the total sample, which is the mixture of both of them. So we will say, first of all, we have to get the number of grams. We have to convert it from milligram to grams. So we will simply subdivide it by 1000. So okay, so it's 0.02698 grams are in 5 ml. So we are going to find the total amount present in 1000 ml, exactly as what we have done before. So we will say this number, we will multiply it by 1000, then we will subdivide it by 5. I'm sorry, once again, 2698 multiplied by 1000, subdivided by 5. So it is 5.3. Then we will subdivide this number by the molecular weight of the acetic acid, which is 60.05. So it is okay, we got the molarity immediately. Okay, 0.089 mole. So this is the molarity of the acetic acid. I'll just continue these calculations for you. So this is unknown, so and from that we got this answer. So now we know that the concentration of the HCl solution in that mixture is 0.113, while the concentration of the acetic acid in that mixture is 0.089 molar.